So good morning, everyone. Today my presentation is about hydrogen-induced intergranular fracture of nickel, cobalt, and chromium medium entropy alloys under in situ hydrogen charging conditions. So as we know that due to a relatively low stacking fault energy and related trip and trip effects, actually medium entropy alloys show excellent mechanical properties. For example, that high strength with very high activities. Therefore, that a series of hydrogen enrichment experiments have been applied for the medium and high entropy alloys. For example, this is one result that with the pre-charged medium entropy alloys, that tested hydrogen enrichment testing under low temperatures. As we can see that almost no degradation of the fracture strain or the other mechanical properties is observed in the presence of hydrogen. And then with the help of the microstructural observations, as we can see that from the specimen surface to the specimen interior, actually a great number of nanotwins and nanotwin structure gradient structure have been formed during the testing. Therefore, that the beneficial effect of the gradient actually overcompensates hydrogen enrichment effects. On the contrary, that if we change the hydrogen charging method from cathodic charging to the gaseous hydrogen charging under 91 megapascal, actually we can see some different results, which means that we can see obviously decrease in the fracture strain of the medium entropy alloys. And if we say that the fracture mode, that actually it changed from the ductile dimple fracture into intergranular fracture, and extensive nanotwins are observed beneath the intergranular fracture surface, which means that it promotes the initiation and the propagation of the brittle fractures. Therefore, that here comes the first controversy. So what is the key role for the nanotwins that form during the testing? It is impede the hydrogen-induced cracking or promote. And then if we focus on the nanotwin itself, actually that several TDS results have revealed that deformation-induced nanotwin is one of the main hydrogen trap sites in the material. It will change that the partitioning of hydrogen during the testing. Therefore, that nanotwins that formed during the testing, especially near the surface, restricts the development of strain localization. Therefore, that some people also observe some ductilization phenomena in the presence of hydrogen. However, since the hydrogen, since the nanotwins is one of the hydrogen trap sites, therefore that hydrogen-induced crack is also observed, initiated, and propagated along the twin boundaries. Therefore, here comes three questions. One is the real hydrogen enrichment sensitivity of the H and MEA. And the second is the effect of hydrogen on the stacking fault energy and related microstructure evolution. And the third is the key role of deformation-induced nanotwins on the initiation and propagation of hydrogen-induced cracks. Here is about the preparation method for the materials. Actually, equimolar nickel, cobalt, and chromium medium entropy alloys is applied in the present research. And the manufacturing process is like homogenization and then cold rolling and then solution treated. For the cathodic hydrogen charging, actually, our proposal is that the nanotwin structure didn't suppress the hydrogen enrichment. Instead, the lattice distortion suppress the entry, diffusion, and migration of hydrogen into the materials. If the hydrogen have some new surfaces for the hydrogen diffusion propagation route, actually, the hydrogen resistance will sharply decrease. To demonstrate it, so both the SSRT for the pre-charged and in situ hydrogen charged specimen are applied in the present research. And this is about the microstructures. So based on the XRD test and the EBST test, we have obtained the single FCC phase medium entropy alloys with an impulsive grain of the average diameter of 30.9 micrometers. And due to a relatively low stacking fault energy, actually the annealing twin percentage is about 41.9. And then we extracted about some green boundary triple junctions and see the element distributions, and we can see the chemical elements distributed uniformly in the matrix. And then we did some slow string rate tensor test. As we can see for the pre-charged compared with the uncharged specimen, almost no degradation of the mechanical properties are observed. And if we say about the string hardening rate, actually due to some continuous trip effects, it offers some steady and string hardening rate plateaus during the test. Well, for the in situ charged specimens, we can see that the fracture strain is sharply decreased, and almost no strain rate plateaus is observed for the in situ charged specimens. And this is about the fracture surface. So for the uncharged and the pre-charged specimens, almost no secondary cracks are observed on the surface. And also that the fracture surface is composed of dimples. Well, for the in situ charged specimens, actually we can say that for the distance increases from the surface into the specimen, actually it is gradually transformed from the intergranular brittle fracture into transition zone and then ductile fracture. And if we enlarge about the intergranular fracture surface, we can see some facet, some secondary cracks, and on the facet and intergranular fracture surface, actually we can see some slip traces along the 111 slip planes. And this is about the observation of the secondary cracks on the interface. We selected this region because both crack propagation and crack retarding is all observed. For example, for the sigma 5 green boundaries, we can see it is propagated, and some KM maps show some string concentration along the propagation route. And why it is propagated, one is about the sigma 5 green boundary, and also for the Taylor factor calculation, we can see that incorporative deformations happens. That's why that propose the propagation of the brittle fracture. And for the sigma 3, we can see that it is blunted, and the height of the blunting tip, it has some string concentrations, and we can see some cooperative plastic deformation between different grains that such cause the blunting of the cracks. And then we have say some sub-microstructures. Since that for the in situ charging, the specimen is fractured at the percentage of 16. So here we first apply some deformation at applied strain of 16 in the absence of hydrogen. So therefore, first we can see some planar slip along 111 slip traces are observed. If we enlarge about the regions, we can see some stacking faults networks is happened. And if except for the stacking faults nets, we also have observed some deformation twins, but the number density is lower. And then we applied the observations for the fracture in the absence of hydrogen. So we can say first is that the extensive deformation twins are parallel located in the matrix. And then except for the deformation twins, actually that we also have observed some HCP laminars. Therefore, that we can conclude that for the materials in the absence of hydrogen, the superior plasticity and string hardening is attributed to the combined effects of both trip and trips. And then that we extracted about the localized substructures ahead of the secondary crack tip for the in situ charging method. And the fracture strain is about 16%. First, because that as hydrogen into the materials, it will sharply decreases about the stacking fault energy and promotes the formation of the deformation twins. Therefore, that we can see extensive deformation twins that located ahead of the crack tip. And then that some dislocation pi-ups is also observed between the deformation twins. And second, if we enlarge about the localized observation regions, actually we can see some very complicated interactions. First is that it has some stacking networks. And in terms of the HALP mode, actually it will promote the stacking force planar slip along different 111 slip planes, which cause some cross sections. And we enlarge about the cross-section regions. It is some cross-sections between 4 laminar HCP phase and some deformation twins. And then we extracted about the microstructures just beneath the intergranular fracture surface. Actually, we can see also some very complicated substructures. First is the deformation twins countered with the green boundaries. Therefore, it will cause some extensive dislocation pileups. And then we extracted about the cross sections that are highlighted C regions. And C regions that with deeper analysis, we can see it's actually some cross sections between HCP phase and deformation twins. And also we observed about some HCP phase together with the deformation twin. And since this can be demonstrated that the HCP phase actually is an unsteady state for the MEA alloys during deformations, but due to the hydrogen trapping behaviors, it will compete the continuous transformations from the HCP phase and to the deformation twin, and it results in this kind of complicated structures. As we can see that we can see a series of nanodomains that inside one grain. Therefore, that we apply some TKD analysis. First, we can see that along some these nanodomain lines, actually it have some spin concentrations based on the KM analysis. And then we have also talked about the orientations transformation around different TKD analysis. Although actually that it didn't show very clearly difference, but with inside one grains, actually it have been separated into a series of nanodomains. And these nanodomains actually, the cooperative deformation is slightly different. And this kind of refinement inside one grain actually will also cause localized hardening. And this hardening will promote the propagation of the intergranular fractures. After that we talk about, because we have formed such complicated microstructures, and we all know that both HCP phase and the deformation twins are important hydrogen trapping site. But the hydrogen trapping behaviors is different because of the localized string concentrations. Therefore, that we apply some GPA analysis. And we can say that for the HCP phase, actually it will cause some tension concentration, and this tension concentration will cause the expansion of the lattice, which cause localized hydrogen concentrations. Well, for the deformation twins, actually we can see a series of misfit points, and the hydrogen tend to trapped at the misfit point. So actually that the trapping behavior of the deformation twin and the trapping behavior of the HCP phase is slightly different. And all this trapping behavior will cause some repartitioning of hydrogen beneath or near the intergranular crack. Such cause very high localized hydrogen concentration and promote the propagation of the intergranular cracks. Therefore, that I have proposed some schematic illustrations. So for the materials without hydrogen charging or pre-charged hydrogen, actually that the hydrogen atoms cannot attend into the materials due to the lattice distortion behaviors. And if that for the in situ charging, actually during charging, it have form some secondary cracks. And these secondary cracks promote some new phase with low surface energies, and hydrogen can transport from this new surface. Therefore, that it has strong interactions with the materials microstructures will cause that some complicated nanodomain structure, and the combined effects of the lamellar and also the deformation twins will promote the initiation and propagation of the intergranular cracks. That's all. Thank you.